Hello, I'm Kimberly Palladino, a professor in the physics department, and I'm joined here by my colleague Dan Hunt, and we'll be conducting a mock physics admissions interview. We're doing this online, and we'll be using the Moreau software for a shared whiteboard for writing on problems. And in the physics admissions interviews, students are asked some basic physics and maths questions. Some of them are quite fanciful, some of them a little more day-to-day material, but it's on topics that a student should be well grounded in, but hasn't quite seen a problem quite like this before in their physics education. And what we're evaluating students on in these interviews is how they think about a problem, how they break it down, how they apply their knowledge, and when they know when to ask for direction, how they can take on board hints to move themselves forward when they get stuck. And a lot of those mimic what happens in a physics tutorial, which is the system that supports students during their studies at Oxford. So with that, let's start our interview. I'm Kimberly Palladino, a professor at the college you're interviewing at. And I've got my colleague, Dan Hunt here, who will be your second interviewer with us today. Hi, Nina. It's great to see you.
Nice to see you. Thank you.
And so we're conducting this meeting online. And so if there's any internet problems, we'll try to reconnect and we'll see if there's anything we can do. If you miss anything I say, please let me know and have me repeat it. And I might need to do the same for you in this modern era. And so we're going to be using the online whiteboard Miro for our interview. And you've got technology to be able to write on it also, and I do too. And so we'll get started. So we're just going to ask you some physics questions centered around a theme, and move on from there as you help solve these problems. So Oxford, as you might know, is a bit of a cycling city. And so I get around by bicycle and I pull children in a trailer, and it's quite exhausting. And so we're going to do some problems related to that. So here I am cycling on my bicycle, and we're going to treat our rider and the bicycle as a single system. So, they've got a combined mass. There's no, forces, of course, a pedal, I'm pedaling the bicycle and the bicycle is holding me up, but we're not going to be able to neglect those effects. So we are moving to the left with our velocity and some acceleration. And there's no air resistance. And of course, we're cycling on the ground. Can you, in this problem, draw what our force diagram for our cyclist bicycle system? So what are the forces? And I've shown you that we are accelerating to the left. What are the forces at play here?
Okay, so let me just switch to try to write. So we said we were looking at it as a combined system, right? So first of all, we have the, oh, that's way too big. Let me correct that. So first we have the combined weight of the system. So this is the gravitational force acting on it, on the whole mass of the cyclist and the bike, times the Earth's acceleration. We have a reaction force from the ground up. And so the cyclist isn't accelerating in a vertical direction. Yeah. We have resistance from the ground. Usually that's on the wheels, but we're looking at the whole system, so it's just some sort of resistance. And then, the cyclist is exerting force on the bike, and so there's a internal force for going forward, I guess.
So there's a force from the cyclist to the bike, but that's internal. So how does our whole system accelerate with respect to the ground?
Oh, it actually does accelerate through the resistance force on the wheels of the bike.
Yeah, so how would you draw that?
How do I? Sorry.
Yep. So how would you, is that, do you already have that shown in your force diagram?
Okay, I can make that clearer. So we have the force, the resistance force acting in this direction on the wheels of the bike, and so turning them in the correct direction.
So if the
I feel like I'm missing something. Yeah.
Yeah. So if the force, if the force is going backwards on the wheel, how can I still move forward if these are all of the external forces on my bicycle? Bicycles, I will say, bicycles and rolling things, incredibly hard force diagrams, and that's why it's your interview question.
Okay. So let me think what I'm missing. We don't have any air resistance. We're moving forward. We have
maybe talk about that force. What's happening where the bicycle wheel touches the ground?
So where the bicycle wheel touches the ground, the bicycle, the only contact point is between the wheel, right, and the ground. The wheel is turning in this direction. So this point here is moving in that direction. So the force is actually in this direction. Does that make sense? It does, right?
Yeah, the force is going to be in the forward direction. Yep.
Yeah.
And at that point, what type of friction force is happening there?
What type of friction?
Yeah, is that point, you've got your errors of motion.
Yeah, it's static friction, yeah. So that's the coefficient of friction times the reaction force from the weight. Yeah, okay.
Excellent.
That makes sense. Yeah, okay.
So do you want to?
Yeah. Sorry.
Oh, we don't need the ground. That's okay.
Yeah, okay.
So, but do you want to add your force?
So I'm just gonna put it in the middle, generally on both wheels, going in that direction.
Yeah. So let's talk about both wheels. Is there? So we didn't draw this detail, but when we pedal, we're pedaling around. There's some gears that attach to our pedal, and it usually just attaches to the back wheel. So our internally applied force is on the back wheel.
Okay, true. Yeah.
So what is happening on the front wheel?
Okay, so let me delete that as well again. So for the back wheel, we know what's happening, right?
Yep.
For front wheel, it is just turning. There's no force from you coming to the wheel. This applies again, this here. So when the wheel is turning, there's again static friction in that single point there. Let me think. I would say that the same force is acting on it. Does that make sense? And so it's easier to ride a bike because you get this additional force which helps you?
Let's think about that. So we've got a rigid bicycle frame. So, our axles, right? If the one wheel is moving forward, the other wheel is moving forward.
Yeah.
But so when the axle moves forward and the wheel rotates, because we've got static friction.
Yeah.
We can have the same static friction with the wheel like turning, either way, or vice versa, right? We can have static friction that applies forwards or backwards when the wheel is turning forwards.
Okay, yeah.
So this static friction on the front wheel, is it forward or backward?
Just let me add, there's another force on the front wheel, which, if that's the front wheel, is just going forward from the frame of the bike, pushing it because of the force applied on the back wheel, right?
Yeah, so that's one of these internal forces to the system.
Yeah. Okay. So we have this force going to the left. And as you said, the whole thing is turning. There is the static point. And what you're implying is that there's friction force going backwards. Let me think why that is. Because what's the difference between the front and the back wheel in terms of the friction? Because the front wheel is turning the same way and it has the same point of contact with the ground, right? It has another force which is applied somewhere in it. So there's another force going backwards, and this is why the whole thing is turning. Okay. It's different. Yeah, okay.
Yeah, so so if I want a simple equation now for my, my acceleration of my whole system, what is that acceleration of my system going to look like? So and you can leave it, you don't have to, you can have that total mass times our acceleration, you can set equal to something else.
Yeah. Okay, so let me just clear things up. So as we said, we have the two wheels which are connected. On the back wheel, we have the friction force going forward. On the front wheel, we have the same friction force. Yeah, the same friction force going backwards.
Well, does it? So it's
Is it the same?
The same force.
I'm sorry, you cut out.
Oh, sorry. Because this is one of the strange situations of how friction and how especially static friction work. Does it actually have to be the same force?
No. Yeah, the coefficient could be different between the two.
The coefficient could be different, but the static force, if I'm I'm holding this pen,
yeah,
and it's sitting on my hand, and I push it really lightly and it doesn't move, and I push it a little harder and it still doesn't move.
Okay.
What was happening with the static force between my pen and my hand?
Yeah. The static friction changes depending on the applied force. Yeah, until it becomes the dynamic friction when it starts moving. Yeah. Okay.
Yeah.
So those are different. Cool.
And so which of these two forces is going to be bigger?
Which of this is going to be bigger? So the friction force on the back wheel is due to the pedaling, and it drives the whole system. So I would expect it to be bigger than the front one. Yeah.
Yep, exactly. So as you said, our acceleration is going to be caused by that rear friction force.
Yeah.
Okay.
And
So so write that all up for our total acceleration.
Oh. I'm sorry, just let me switch around stuff. Okay, so yeah, the other two forces on the front wheel are internal from for the front wheel. So the whole bike rides forward because of this friction here. And if the mass of the whole system is A, this is what we have for the driving force. Yeah.
Well, that's our driving force, but what's our total force on the system?
Yeah, okay. So we have the driving force on the back wheel. On the front wheel, we're talking about the horizontal acceleration, right? Yeah.
Yep.
Yeah.
Yep.
On the front wheel, we have the force which comes from the frame, this one here, which pushes the forward, the other wheel forward. And that force should be the same as the friction force on the back wheel, so that they both accelerate at the same rate. Does that make sense?
Yeah, when we talk about these internal forces, it becomes so it becomes a little convoluted. So let's talk about just the forces external to the system. You already have them there. You're just missing it in your equation.
Okay, I'm missing something.
So we've got our force from our pedaling that's pushing us forward on the back wheel, and then we said we have a slowing. We have a force in the opposite direction from friction on the front wheel.
Okay. Yeah. Cool. Yeah.
So our total accelerating force needs to take into account both of those.
Yeah. So yeah. There we go. Because they're in different directions. And the acceleration is forward.
Yep.
If we assume the acceleration is forward, yeah.
Yep.
Okay.
Fantastic. Okay. So that's our situation on a flat surface. So now I'm going to ask you to do the same thing, and we might have to be careful with our drawings. I'm going to move. Oops. I'm going to move. Oh, I want to. Sorry. There we go. If I want to, okay. If I want to move, how do I move along the screen now?
You have to select the cursor up top. Where, yeah, there we go.
There I go. I was just touching too close to any of our writing before. Yeah. There we go. Okay. So I'm going to go back. So now I'm going to draw a situation. And I'm going to have my same cyclist on a bike. And they're now going to be on an incline. And they're going to be pulling a trailer up the incline. So now we've added something else to our system. Can you draw, and we are still to stop. Now we get to go, but now we have to go up a hill. Can you work towards solving what that total, the force that's going to give us our acceleration up the hill is now in this system on the hill?
Yeah. Okay. So we'll be looking at the projections of the forces along this line so that we, don't look at other projections up and down. So we still have, let me just fix this. We still have the forces, we still have the friction forces on the wheels as the starters. Nope, the other way around. I'm gonna delete your hill though.
That's fine.
Okay, I mean, yeah. We still have those forces, however, they are smaller. Okay, let's come back to that later. First of all, right now, the weight of the whole system, there's a projection of it along the hill slope in this direction, which is sine theta times the weight which we had, right? Yeah, we also have now the weight of this thing, which will denote with a small m. And we have its projection as well. What else do we have? We have friction on its wheels, which following the same logic for the front wheel, the friction here goes backwards and it's dragged forwards by the friction on the back wheel of the bike. So we'll call this F double prime. We have F prime here and F here. Is that all? Is there something else new coming from the setup?
Nope, I think that's
Yeah.
good. Everything else would be internal to the system.
Yeah, exactly. Okay, so our final equation of motion would be m plus small m. They're riding at the same acceleration, equals the driving force minus the two friction forces minus the two projections of the gravitational force. Okay. Yeah.
Now, let's go back to something you started to mention before. How do our F and F primes relate to our forces before when we were flat? What will be different for those forces now, our frictional forces?
Okay, so those frictional forces are some coefficient times the reaction of the ground. This time, when we have an incline, this is the system. We have the weight or the gravitational force going downwards. We have some projection of it in this direction. And so the reaction force from the ground is smaller going upwards, compensating only for this component, which is the cosine theta of mg, right? Or m plus small mg. So those friction forces will be smaller this time, but this is for the F prime and F prime and F double prime. The driving force, however, yeah, it depends on the drive. Yeah, it depends on the power input. So to keep driving with the same acceleration, you would need a larger force. Yeah, because those components here become small. Wait, what? I said those components will become smaller. Yeah, but we have those components. Okay, yeah.
Yep, you've got it right. Excellent. So let's maybe put some numbers to this a little, but I'll do very, very easy numbers.
Okay.
Unrealistic numbers, one would say. So let's assume that oops. So, our G can just be a perfect 10 meters per second squared. And let's say our theta is 0.1 radians, which is about 5.7 degrees. Our big M is going to be a whopping 10 kilograms. I was on a diet. And our little m will be 6 kilograms. And our coefficient of static friction for all of these is going to be a half.
Okay. So the idea is to calculate the driving force. Yeah.
The idea is to calculate the driving force or the resulting acceleration.
Yeah. Okay. We're looking at the second scenario, right? Yeah. We have the.
Yeah. Let's look at our second scenario.
Yeah. So our acceleration times those 16 kilograms will equal the driving force minus the two friction forces. Now we have a coefficient. Oh, yeah, okay. Let's just put in the numbers. We have the coefficient. I'm fixing the width. And I said that one of them was a cosine theta times yeah, times the acceleration. So one of them is for the big mass, the other one is for the small mass, right? So this is the coefficient times the projection of the gravitational force for both of the masses. And then we have sine theta.
Oh, I forgot to give you a number.
Yeah, I thought so. Okay.
Which is our your little f.
The driving force. Yeah, applied force. Okay.
And that's going to be 400 newtons.
Okay.
And here I'm loosely calling it the applied pedal force. There's clearly
a lot.
There's more, right? We'd be dealing with our gear system in talking about our actual pedaling force. But so this is the equivalent number that you wanted of what's along the ground. Yeah.
Okay. So we have the acceleration, gravitational acceleration, and then the sum of the masses. I'm putting in numbers kind of partially. Sorry about that, but you follow.
No problem.
Yeah.
So with an angle like this, how can we quickly figure out the sine? Let's do the sine first.
Yeah. So we have 5.7 degrees. We have 0.1 radians, and we're looking for the sine of that, or the cosine.
Yeah,
let me think. So 0.1 radians.
Is this a big angle or a small angle to have to
small angle? Yeah.
So what often there's a small angle?
Oh, yeah. We can use an approximation that sine theta is approximately the value of theta in radians, and then cosine theta is approximately 1. Yeah, thank you. That's all right, right?
Yep. Yeah.
Okay. So if we plug in the numbers, we have that 16 times our acceleration, which we're looking for, equals those 400 newtons minus 0.5 times cosine is 1, g is 10, this is 16, 160 divided by 2 is 80. So we'll just put this in. And then minus the sine times 160. The sine is 1/10, so that's 16. So our acceleration will be 320 over 16 minus 1, which is 19 meters per second. And I think everything's in kilograms, it's in SI units. So that's our.
Yeah, great job checking your units. And actually, quite conveniently, because of how you've written it, what would have been our situation on the flat ground compared to this?
So on the flat ground, we wouldn't have, we wouldn't have the sine theta argument at all. And the f prime and the f double prime wouldn't have the cosine. But the cosine is, we take it as 1. So it's the same. So we just don't have the last term, which is 1, which isn't a big difference.
Yeah, we ended up with, flat. Yeah, so numerically flat, we'd be at 20 meters per second instead of 19. Now that's a little bit due to the numerical choices here.
Yeah.
But it, my legs certainly feel more tired than that.
Yeah. Okay. Cool.
Excellent. Let me briefly ask you one more question.
Yeah.
So now, let me move us over again. Okay. Sitting still. And I'm going to simplify it. I'm not going to bother to draw the front wheel. I'm actually just going to draw the pedals. So
Okay.
the pedals are 180 degrees off, so they're up and down. And now I'm going to come in and I'm not, I don't know, that would be darker. I'm now going to push against that bottom, sorry, I'm trying to show it turning, that bottom pedal. I'm going to push it backwards.
Yeah.
So we've got a bicycle sitting there. And usually when we pedal, you know, in this view, we would pedal around clockwise. And so in usual pedaling to move forward, that bottom pedal moves backwards and the bike moves forward. But now I'm not sitting on the bike. I am an external to the system. And I push that pedal backwards. What's going to happen to the bicycle?
Okay, we push the pedal like forwards, right? So that it rotates in the wrong direction.
Well, the way the way the arrow is shown.
Yeah. Okay. So what will happen? Both of the wheels are on the ground, right?
Both the wheels are on the ground. We can
Yeah,
add them to the picture if we need to.
Yeah, we have the. Why don't we have the back wheel? Okay, let me think. So first of all, are the pedals when they turn, they're turning this chain here, right? Oh, yeah, the one I just moved. And the chain starts going in that direction. Yeah. And so this, the chain is connected to some, not sure how a bike works, to some inner part of the wheel, of the front wheel. So this smaller circle here turns in that direction. So this is the whole bike, right? Yeah. It's not some complicated system. Yeah, okay. So this wheel should be turning backwards. How is the back wheel connected to all of this?
This is the back wheel. So the front wheel is just like a free spinning wheel. It's attached to the
This
frame.
is the back wheel.
But this is the middle part is the gear system that the pedal is attached to. So the pedal attaches to the back wheel, right? Our pedaling
exactly.
turn our back wheel. But now we're not on the bike doing the pedaling. We're just a person standing next to the bike pushing.
Okay. I'm trying to see the difference between us standing on a bike and us not being on a bike.
Well, yeah. So let's.
Obviously, the weight is the beginning.
The weight will be part of it.
Yeah.
What else? What can be happening? So what other external force? I've drawn only a very small part of the system. What other force can be acting on this bike, right? Because we're trying to say, you know, how is this bike going to move? It was still, and we're pushing on a pedal, so we expect it to accelerate in some direction. So it'll start moving in some direction. What other forces could be applied? You know, what other external forces are going to be acting on this bike system? And here we just care about this rear tire that will affect which direction this bike goes.
Yeah, okay. I'm trying to think. So, yeah, we know about the friction force on the back wheel, again, going in this direction because the wheel is turning in that, yeah. We are not sitting on the bike. Let me think. What is different between the previous setup and this setup. The only difference is that the force is coming from an external place. And this time we're looking at the system by its parts, so we're looking at the pedals. So the force is applied here, and there's a torque around this point in the middle of the pedaling gear.
Yep. So we could, I think, let's try and we could analyze this through the full torques, and that would give us our full understanding. And I think I'm going to try and have you leap over that to just think about in this situation, how should we be thinking about our different forces?
Yeah, okay, so in the pedaling gear, we're applying the force from outside. We're pushing the bottom pedal to the back. And with this, apart from turning it, we are also applying force on the whole system, which is it resisted by some, or could we say that we are just applying? Yeah, so apart from turning it along its direction of rotation, we also apply some projection of our force straight to the left of the system. Yeah, so effectively we have some force going to the back of the bike's acceleration if we want to accelerate it forwards. Okay.
And we've got only
That's
static, and on the back we only have static, we have the extra sub part of the force, that pedaling force that we would have had in the first case, pushing us forward. But is it going? So the
yeah. I mean,
I think you've gotten most of the way there. If I just have a bike,
if you imagine a bike and you just try to turn the wheel, you're probably going to push it backwards.
Exactly. So this is now you can amaze your friends and family and anyone standing around with a bike. It's actually called the bicycle paradox, that we're used to thinking about pedaling our wheels, pedaling, and that would move us forward. But if you apply this force externally from the system, it'll move it backwards.
Okay. Yeah. Nice.
So, and none of our friends and family are really amazed by this, but that's what happens when you're physics. Cool. Well, thank you so much for answering bicycle questions and working on some physics problems with us today. So this will conclude our interview, and we'll move on.
See you.
Thank you so much. I'm Professor Palladino, and this is my colleague, Dan Hunt, and we'll give a brief review of the interview you've just seen as a physics interview. So this is an approximate question of an Oxford admissions interview question. And our student, Nina, is a third-year Oxford student who had never seen this question before. And overall, she did an excellent job. And I'll ask my colleague, Dan, to give his impressions of the interview first.
Okay, I think that Nina handled the question very well. There were definitely some points where she was grappling with the kind of material that we were discussing, in particular with the bike paradox, but she was then very quickly able to rehabilitate and reorient to understand what we were actually asking with the question. With a lot of topics such as these, we're not looking for people to get the question in an instant. We're looking for people who are very quickly able to understand and adapt to the situation, and who seemed very eager to kind of pick up on the topics that we're actually discussing. So I was very impressed by how that was handled and how we came to a solid answer right at the end there. Absolutely.
Yeah, I agree. I think Nina did a really wonderful job, and really very much what we expect. And, even talking to another professional physicist, when you first start with a brand new problem, you might not see all of the effects that are going on. You might have to ask questions to better understand the setup and why you're being asked the question. Her process of verbalizing everything she was thinking and including drawings of how she was thinking about things really let us have a really good sense of how she went about tackling the problem, and that really lets us evaluate her knowledge in a strong way. It helps us give her feedback about what she's thinking early on, so that she can maybe adjust her thinking. And that's, again, our interview process lets us as future tutors to a student think about what the tutoring process would be like. Does the student know when to struggle with an idea, when to maybe ask if they're going in the right direction, and when to use a hint correctly to move them more forward? And Nina did a really wonderful job in all of that. She would be near close to perfect marks, maybe a student who is a little bit faster through everything, perhaps especially with the first bicycle on the flat ground and what happens to the front wheel and the fact that its frictional force is opposing our direction of motion, is maybe the type of thing that we would, if a student got that immediately, they would score a little higher. But almost in all cases when that happens, it's because that student has maybe worked on a bicycle problem before and already knew that that's the situation, because that's how these physics problems usually work. We want to see some general math skills, so you don't need a calculator, but you might have to do some simple arithmetic or basic variable manipulation, maybe a bit more than was shown here. But we're really trying to give students in an interview a question where they should know enough to go in and solve it, but it's a brand new question. And Nina handled that really well in how she interacted with us and with the Moreau whiteboard.